So this week it's my pleasure to introduce our speaker, Alekh Agarwal. We are really delighted to have such a real superstar talking at our seminar this week. So Alekh did his PhD at UC Berkeley under the supervision of Peter Bartlett and Martin Wainwright, who's doing really amazing work in the intersection of machine learning, stats, and optimization. He did like a lot of spectacular work in these fields in online learning and optimization. Some very, very memorable papers in that domain. After that, he did a postdoc. Well, I guess like he was spending his time mostly as a postdoc in Microsoft Research New York. I don't know if that's right. He's going to correct me later, maybe. And recently, he's been in Redmond, same thing at Microsoft Research, where he's leading the reinforcement learning group as a principal research scientist, or principal research manager, that is. And he's been getting into reinforcement learning in past years and bombarding us with wonderful papers on this topic. And one of these is this PCPG paper that he's going to be presenting today. I'm really looking forward to this. So please, Alekh, take it away.
Yeah, and let me thank the organizers, Sham and Chiara, for first of all, this awesome seminar series while we cannot meet in person, for inviting me, and for the over-the-top nice introduction to Gergo. So like Chaba said, since I have a hard stop at 11, we'll try to keep this more interactive. Feel free to raise questions during the talk if something's not clear. And the talk today is going to be about a recent paper that's going to be appearing at NeurIPS, which is on adding exploration to policy gradient methods. And this joint work with Sham Kakade, who's at University of Washington and Microsoft Research New York, Mikael Henaff and Vincent, who are both our postdocs and have since moved on to Fair and Cornell, respectively. So, probably most people are familiar with the basics here, so I'm going to go pretty quickly over the initial stuff. The main motivation for this work, or the starting point, was that there's a lot of interest in policy optimization techniques fairly broadly. They are being looked at pretty closely empirically for a variety of reasons. That they're easy to work with in the sense that if you can differentiate through your policy parameterization, you can invoke these methods, which plays really well with the deep learning stacks. They naturally apply to discrete and as well as continuous states and actions. And you're not really optimizing some surrogate objective, but usually the objective of interest, which is the value of the policy that you care about. So even if you don't do the best possible job, hopefully you find some reasonable local optimum of that objective since you're doing optimization. And that this has not just been a practical curiosity. Of course, there's been a fairly significant and growing body of work on understanding when policy gradient methods work, how well they work, the quality of the solution you find, and how rapidly you converge, etc. And while this is, especially this literature has come into its own in the last maybe 2 to 3 years, if I had to distill it down to one kind of core idea, it would be that if I take my agent and make sure that the initial state that I'm starting it in is sufficiently randomized, is sufficiently diverse, sufficiently exploratory, then under some potentially reasonable conditions, these methods will find a near globally optimal solution. Now, on the one hand, this is very striking because these are, non-concave maximization problems. So the fact that you're able to do something at all is quite appealing. At the same time, this property that you need a sufficiently exploratory initial distribution is still a pretty severe assumption if you think about the main challenges in reinforcement learning, where exploration is usually a pretty central challenge we worry about. And this is, again, not just a figment of theory. We see this also in practice, where techniques like domain randomization to make sure that you're being sufficiently exploratory are pretty front and center in the literature. Right. So the question we wanted to ask was, can we, by design, add exploration to policy gradient methods, just like we've figured out ways to add exploration to model-based and Q-learning style methods in a long line of works in reinforcement learning. And this paper takes a step in this direction. So in the talk, I'll go initially with some quick overview of policy gradient methods and some basic results that we'll be building on, followed by the PCPG algorithm and its theory. And then I'll, assuming I have time, also go over some of the empirical evaluation. So we'll be in the discounted MDP setting. So we have a discount factor gamma and 0, 1. We have, because we are doing policy optimization, we will take randomized policies, so mappings from states to distributions over actions. One concrete MDP model, which we will talk about a fair bit on and off, is what's been called a linear MDP. This has been this model has been introduced and reintroduced many times, and was most recently popularized in works of Chi-Jin and co-authors, as well as Lin Yang and Mengdi Wang. So the linear MDP is a structural assumption that the transition probability P of S prime given SA, this factorizes as some features of the state action pair SA and some features of the future state S prime, and you take an inner product. Typically, these both of these vectors are assumed to be d-dimensional, but for this work, we will allow things to be infinite dimensional, so everything can live in a reproducing kernel Hilbert space. And because the transitions themselves have this nice linearity, almost all quantities of interest end up being linear in a linear MDP, whether it's value functions or similarly optimal and near optimal policies. So in particular, natural policy class will focus on with linear MDPs is this log linear policy class, where we apply a softmax transform to a linear function with function with parameters theta with features phi to get probability of A given S. Okay, and the goal, as usual, is to find a policy that maximizes the expected reward in some chosen initial state as 0. And note, I'm kind of deliberately putting as 0 rather than a distribution over initial states here, because I want to say that we will not assume anything about exploration in the initial distribution. We will actually really explore the MDP by design rather than by assumption. And so it's okay if the initial state is a point distribution. But of course, everything works if you have an actual distribution over initial states as well. If it doesn't have to be deterministic. Okay, I'm assuming that things are clear. If there are questions, please feel free to interrupt. Okay, so
Alekh,
yes,
I think that this will become clear. But this goal that you're starting, this fixed initial state, maximizing the value, you're talking about the learning setting. But it's going to be like the reset or finite horizon or whatnot setting. Is that right? Or is it?
Yeah, it's not one long trajectory. That's right. So you can basically mentally think of, as usual, that with probability 1 minus gamma, the agent gets reset to the initial state as 0.
Okay.
Right. Good question. Okay, so one algorithmic building block that we will use is the natural policy gradient algorithm, which was introduced by Sham Kakade in 2002, which is basically a specific preconditioned first order gradient method to optimize the objective that we saw on the previous slide. But in order to talk about NPG, I do need to now, just for a very brief period, introduce a distribution over initial states, and then we'll take it away. Okay, so just for starters, let's assume that somebody gives us a distribution rho over the initial states. This is only for the algorithm, not for the goal that we actually care about, just for this NPG algorithm. Okay, then what NPG would do is it will basically perform these updates on the policy parameters theta, where it computes the gradient of the current value function, scales it with a preconditioning matrix that's a Fisher information matrix. The exact form is not going to matter here. I'm going to show in a minute. So the particular, while NPG looks potentially complicated at the first glance, if we specialize down to linear policies, the log linear policies we just saw, it takes a much nicer form. It takes this very kind of convenient soft policy iteration form, where you go from the current policy pi t to pi t plus 1 by just doing this multiplicative rescaling with some direction wt in a product with the current features for a particular state SA. So sorry, I should have had pi t plus 1 of A given S is proportional to pi t of A given S times this quantity. And the main thing you need to specify is what is wt. What is that's effectively the descent direction now, or the ascent direction. And the way you can obtain wt is by solving a least squares problem, where you ask, okay, so I have my policy pi t. It induces a q value function. I'm going to call it qt. And it also induces a distribution. So it also induces a distribution over states and actions when I start in rho. Okay, so I take my initial state from rho, and then I take all actions according to pi. That induces some distribution over states and actions. I'm going to call that dt subscript rho to denote the dependence on initial state. And the least squares problem I solve is I draw states and actions from this distribution that the policy induces. And for under that distribution, I try to approximate the q value function of pi t with a linear function. And wt is the best linear fit. It's the best linear approximation to qt for this distribution over states and actions under a norm constraint. And what you can show is that this is exactly equivalent. That if you plug in this exact minimizer to this least squares problem in this update rule, then you get NPG precisely. And if you want to do approximate NPG now, maybe sample-based NPG, that already suggests what you're going to do. You're not going to solve this least squares problem exactly. You're going to solve it with samples to approximate the expectation. You're not going to obtain the exact minimizer. You'll do some numerical optimization to approximate it, and so on.
It's a quick question. So I know this theorem. This is policy gradient theorem, right? Like in a way for the unconstrained form.
Yes.
And then you're just saying that, well, since it's about directions, we are exponentiating whatnot. Doesn't matter. Like you put a constraint on the.
Oh, you're talking about the norm less or equal to 1 constraint.
Yeah.
Yeah. So okay, that's a great point. So if I wanted to get exactly the NPG direction, I'm being a little vague here. Then I would say basically minimize the norm of W, subject to subject to a small least squares loss, for instance, or I would take kind of the ridge regression solution instead and drive the ridge parameter to 0. Yeah, so right, because that's what gives you the pseudo inverse. I'm saying, okay, so if I wanted to get exactly the NPG solution, the best way to think about it is, rather than putting the norm constraint explicitly, I would add an L2 penalty and drive in the limit of driving the penalty parameter to 0, I will get the NPG exactly.
So there are two things going on here. I think, like, one is the inverse that you're talking about, that the inverse may not exist, in which case you will have to take pseudo inverse, which you can approximate with the ways you describe. That's one thing. The other is that there is some scaling of the update rule of the policy nice, so that maybe the from that perspective, setting the step size, the eta parameter, it's like maybe you want to impose this normalization anyways.
Oh, I mean, but that's sort of a bit more subtle, because, you know, of course, the scaling is not going to be necessarily identical at all rounds, right? The minimizers for different pi t's can have different scales potentially, but you know, so this is, once I add a norm less or equal to 1 constraint, specifically once I put the constant 1 there, I'm no longer exactly recovering NPG necessarily. And this is just then an NPG-like update that is inspired from the exact version. But it basically satisfies the same theoretical properties if you assume that things are appropriately bounded.
All right, Alek, I have another question here. So, like, is this squared loss also a consequence of this whole MPG theory, or this is just something that says, okay, I'm just gonna start with a realizability assumption, and then say that, well, this is gonna be 0 if my W corresponds to my Q, and then I just use the squared loss? I really
that's a good question. So the way the reason squared loss really is very natural here is basically, if you think about what the Fisher information is, okay, then the Fisher information in the exact rule is, if you write it down for the linear case, it's basically going to be feature covariance, scaled feature covariance. And now if you're asking that I want to get sort of feature covariance inverse times something, like it really ends up being, so if everything were invertible, right, then this is, it's just that the least square solution is exactly the A inverse B type of thing that you get in NPG, and the A and the B, the way you get this particular least squares problem is you match the A and the B to what you need.
All right, perfect. Yeah, that makes perfect sense. Thank you.
Yeah. No, but that's if I were going more into the details of NPG, I would definitely be giving that intuition, but that's certainly the way to think about it. Okay. Sure. No, but if there are other questions, or we can move on.
I had a quick query with respect to the coverage of the distribution. Yes. Is there some sort of boundation here?
So there is going to be an assumption on the coverage of rho that we'll talk about in just a moment. Okay, so I'm gonna before we can talk about what we want to do to build an exploratory PG algorithm. It's of course important, like what role exploration plays in the convergence theory, and so we'll talk about that in just a moment. And there we are. So if we try to analyze what NPG, and in particular these log linear policies, does, then you get basically the following result, that after t iterations, so for any comparison policy pi theta, which is again linear policy, log linear policy, you can bound the regret of the best parameter in the sequence of iterates you've obtained by the expression shown on the right here. And the first term is nice and innocuous. It's going down as 1 over square root t. It has some horizon dependence, but nothing really troubling there. The second term is where we start to get into more exploration-related questions. So the constant kappa here, I'm not giving the exact definition, but you can think of kappa as basically the smallest eigenvalue of this covariance matrix, of the feature covariance matrix under the exploration distribution rho. Right, so this is saying that if the initial state distribution that you had induces a full dimensional covariance in the feature space, then you're okay. Then this term will be well behaved. But if there is even one direction you missed out on, this can be problematic. Now, I said we want things to work with infinite dimensional RHS as well, and there, of course, you're not going to have full dimensional covariance, of course, or even all eigenvalues are not going to be large. You're going to have spectral decay, but there is kind of a, that's why I said kappa is related to, but not exactly equal to the smallest eigenvalue. More generally, there is sort of a relative condition number type quantity that comes up, which measures the conditioning, the amount of mass rho puts in directions which the policy pi theta that you're comparing to would visit, and there is some cross condition number that way. But let's just think about the simple version for the most part today. Okay, and this also depends on the number of samples. This piece n that you use to solve the regression problem. So like I said, we obviously cannot minimize the expectation exactly. We're going to approximate it with samples. And if you use n samples, then this is the dependence on n. So that's at least good. It's going down. It's n to the quarter instead of 1 over root n, which might seem odd. And that's currently happening because I want to get a dimension-free rate for scaling to ArcHS, and so I'm losing something there. And if I'm willing to pay, I can get a d over n instead, which will give us overall square root. Now the third term is a bit more subtle, and epsilon bias is something that really starts to measure. So I said we're gonna, for some parts, rely on the linear MDP assumption, and this is the first place where it comes up. The point is you're trying to take the Q-value function of pi t, and you're going to try to approximate it with a linear function. Well, there is no reason in general you can do this thing well, right? And you might have a large approximation error here. And that can actually cause problems. So the third term measures basically, on the other hand, we know that if the MDP is linear MDP, then the Q-value functions for all policies can be written down as linear functions. And what epsilon bias measures is a particular notion of violation of the linear MDP assumption. And I don't think I'm going to dig into it here. When we go to the actual PCPG theory, we'll visit this in much more detail. But for now, just think of it as epsilon bias as measuring basically how much error you incur in approximating Q-value functions with linear. By the way, the result that I'm presenting here for just the vanilla NPG result, it's also very related to the results in the Politex paper involving Chaba and who's here on the call.
Can I have a quick question, Alekh?
Go ahead.
So the theorem is stated for all theta with a norm less than or equal to 1. Mm-hmm. How does the bound scale with the norm of theta?
I do not recall off the top of my head, but I'm sure it's not exponential. It's going to be polynomial. Okay, but I could not tell you the exponent off the top of my head.
Okay. Yeah. All right. Thanks.
Okay. So like I said, there is this initial distribution assumption here. So now we understand, we can get into this a little bit more because this is really the exploration assumption, right? So we are assuming that we are given an exploratory distribution that induces a full dimensional covariance in the feature space. We also do know that if we were just running natural policy gradient without any assumption about the initial distribution, we are in trouble. Why should we be in trouble? Because if you just think about this sort of simple chain MDP, and I've shown a particular version here on the slide, if the only time you get rewarded is when you go all the way to the right and you start in the S0 on the left here, under most policy parameters, you have a vanishingly small probability of getting to the rewarding state. And if you never really get to the rewarding state, you get no gradients. And you just cannot, without observing an exponentially large number of samples from the policy, you just will not make progress. So we know that if I'm not doing anything special in the algorithm to address this case, then I'm going to need some condition on rho. But the point is, should I assume that condition on rho, or should I, like I said, do something special in the algorithm to try and ensure that I'm building increasingly better and better condition covariances under rho by doing active exploration rather than by assuming it away? And that's really the starting point for thinking about PCPG. Okay, so I'm going to switch gears now, and I'm going to start talking about PCPG itself. So if there are any remaining questions on NPG or the first part, this is sort of your last chance. Okay, great. So PCPG stands for policy cover, policy gradient. There are two, so the policy gradient part we've been talking about already. So the new concept we're going to be leveraging here is what we call a policy cover, which is really an ensemble of policies, that all visit diverse directions in the feature space, phi. And the role these policies will play is they will help us to construct increasingly better initial distributions to start our policy optimization from. So in particular, what we'll do is, I'll talk about how we construct this policy cover in a moment. But at any given point of time, if I have a particular policy cover, I will say, okay, so each of these policies in the cover, they will have the distribution over states and actions that they introduce. And the initial row that I will use for doing policy optimization is a uniform mixture of the policies in this cover, right? So what that means is anytime I want to draw an initial state for the agent, I will pick a policy uniformly at random from my cover. I will execute with sort of gamma discounting this policy. So I will always sort of continue with gamma, terminate my roll in with probability 1 minus gamma, and see which state I land on. And that's going to be the initial state for a run of the algorithm, for a trajectory that the algorithm would like to draw. Okay, so this policy cover better be exploratory if I want my initial distribution to be exploratory. And the way I ensure that the policy cover is increasingly doing more and more exploration is by leveraging a fairly old and trusted set of ideas in MDP exploration literature. We're going to be optimistic in the face of uncertainty, and we're going to be doing this, partitioning of the state action space into known and unknown sets in the style of construction which was really pioneered starting from E-cube style algorithms. So in particular, what we will qualitatively do is all the directions which this policy cover visits sufficiently often, we will intuitively think of them as known, because we have a way to get to those directions. We have a way to get these directions into our covariance. All the directions which are not in the known set, we don't necessarily have a good way of getting there, and we will provide ourselves an exploration bonus to try and get there. And then we will run policy optimization with this bonus to hopefully find a policy that can get to one of these unknown directions. And remember, the policy optimization will be started by taking the initial distribution from the cover. So that's kind of very high level. Let's try to make it a bit more precise now. Okay, so there is some initial policy we start from. The first thing one of the things we'll always do is we will, because we measure the quality of exploration through the feature covariance matrices of things, we will be constantly maintaining estimates of the feature covariance for the policies we are constructing. So we have some initial policy pi 0, which we just take to be uniform over actions in every state, and we estimate its feature covariance. Now the algorithm executes a set of epochs. In each epoch, it has a particular policy cover it's working with. So initially, that's just the first policy pi 0, and it grows over time. At some epoch I, you have some. Oh, sorry, this should have been I and not n. You have some. You have I policies in the cover, and you take the initial distribution to be their average, which like I said before, you pick one of the policies from the cover and you execute it, and that supplies you with the initial state. And you also maintain the average covariance along with some regularization, which basically represents the covariance of features you get when you execute when you sample states and actions from the cover. Okay, so I have the cover and I have an estimate of its covariance. Using these two objects, I can define my known set in the following manner. So a state action pair is called known if its features have a small quadratic form in the inverse covariance of the cover. Okay, and the way to think about this, if you've seen linear bandits or linear MDPs before, this should look very familiar. The way to think about this is if a direction phi is visited sufficiently often by my current policy cover, it will probably have some non-trivial quadratic form in the covariance matrix. The covariance matrix will have some adequate representation of this direction. And conversely, when I take the quadratic form in the inverse covariance, that's going to be small because the quadratic form in the covariance is large, right? So if my current policy cover gets to a direction often, I should expect a small quadratic form. I call this direction known. And beta is some threshold parameter. It's a hyperparameter of the algorithm that we use to decide what's known and not. For things that are not known, like I said, we give ourselves an exploration bonus, and the exploration bonus on those things is 1 over 1 minus gamma, which is the largest cumulative reward you can hope to get. Having defined this bonus, I now take my initial distribution, which is the uniform mixture of policies in the cover. I take the bonus augmented reward function, and I give them to my policy optimizer, which in this case would be NPG. And I run some appropriate number of iterations of NPG, solve to convergence, whatever. That's again how many steps you run ends up being a hyperparameter. You run NPG for some time, it outputs a policy, and that is a policy you take and you add it back to the cover, and then rinse repeat the whole process, right? So that's the algorithm. Any questions?
Just a quick clarification question about this last step. So this is where the algorithm is going to interact with the environment, right?
There is, in the proof sketch, I'll talk about it. There are 2 places of interaction happening. So when I'm constructing the covariance of the policies as well, right, I need to sample states and actions from the policy stationary distribution. But of course, in the NPG step also, there is a lot of interaction with the environment.
Yeah. Couldn't you just do both at the same time when you're running MPG?
Great question. And there is a lot of optimization to be done on the sample complexity side, and we are working on it. Yeah. I think but this is kind of the simplest and cleanest version. Yeah.
I had a quick question. Maybe I'm wrong, but wouldn't the sign here, where you have defined the known set ki, in the end will be greater than equal to the threshold value? Just a clarification.
No. So if so imagine you only visit one direction, okay? Then sigma is going to be basically aligned with that direction.
Okay.
Which means when you take phi transpose sigma inverse phi for that direction, you're going to have a very small projection, right? Because phi has a large eigenvalue in that direction. Phi will have something like order n eigenvalue in that direction if you're accumulating n samples. So phi inverse is going to have a 1 over n eigenvalue in that direction. For all the other directions that you don't visit, if you take the quadratic form, well, that will basically be like 1 over lambda. Just because the ridge regularization is the only thing keeping this thing from being infinite in those directions. Okay, right? So it's going to be large in the directions you don't visit, small in the directions you visit. And in fact, just to hammer home that point, you can ask yourself what this looks like in the tabular setting, right? Where your features now should just be one-hot indicators of the state action pair. They should be state action dimensional vectors. And there exactly reduces this definition of known set to saying which are the state action pairs which your initial distribution puts a sufficient probability on. Okay, so it really is consistent with that intuition. Excuse me.
I do have a question still.
Yeah, go ahead.
About this NPG and the way this algorithm is resolving exploration. Because if I'm thinking about a chain example, the signal is going to come from, I guess, okay, so the way it works, I'm just trying to imagine how this known set is being used here. And so the way it seems to be used is that maybe you have a fringe and then you're exploring more.
Yeah, okay.
Like,
So
you have to have a random chance of encountering new states where you haven't been. And that was my struggle of like imagining, like, will that happen frequently enough, or like?
So let me mention an important thing, Chava, which probably clarifies a bunch of this, which is not on the slide. So one important detail is in the unknown states, or in any state where there is at least one action such that the state action pair is unknown available, I'm always uniform over the state action pairs, irrespective of what the policy says.
Okay, good.
And this is sort of like, if you remember E cubed, it has this balanced wandering step, right? It's very much like that. And that's actually critical because yes, you have your frontier of what's known, and you want to basically expand that frontier at least by one step always. And so that uniform exploration is actually quite crucial to make sure you do that expansion. Otherwise, yes, you would be in trouble.
Good. So it's like NPG prime or something like that.
Yeah. Right.
Okay.
No, absolutely. Yeah, but that's a very important question. Anything else?
Yeah, so I was going to say that, well, this bro I, so this is like the state distribution of a mixture policy, right?
Mm-hmm.
So I guess this covariance must be like pretty hard to estimate, actually, right?
Why? You can just remember this is a trajectory level mixture. So so the way you get rho is by picking a policy at random and drawing a state action pair from its stationary distribution.
Right, which means that you just randomly draw a policy, then you run it for a long time, and then you just draw another policy, run it for a long time again. So like every sample that goes into this covariance matrix is like sort of expensive. Right?
Yes. So the way to think about it is, if you have the covariance matrix for each policy individually in this mixture, then the covariance of the mixture is just a mixture of the covariances.
Right. Oh yeah.
Okay.
Yeah.
So that's what we do now. I do not want to at all suggest though that this is a cheap operation, and actually we lose most of our sample complexity in covariance estimation.
Okay.
That's quite expensive.
All right, perfect, very good, thank you.
Okay, so if there are no further questions, let's talk about what the algorithm does. And for simplicity, let's start from when the linear MDP assumptions are perfectly satisfied. And in fact, for even more simple, let's first just think about the linear MDP as being a finite dimensional linear MDP. Then what we can argue is that this algorithm, I'm still using an old name for the algorithm here, sorry. Forgot to correct this one. It uses samples as well as computation, which are polynomial in the dimension, 1 over epsilon, horizon, etc., and all the relevant problem parameters, basically, and outputs an epsilon suboptimal policy. And pi star here is the optimal policy that we're comparing to. Right. So the nice thing is that this is under S0. There is no dependence on the some kappa type initial distribution based quantity. On the other hand, there is a reason this slide says poly, right? Like, we all do theory. If somebody shows you a poly, that means that the precise dependence is probably not particularly nice. And it's certainly the case here. And I'll talk a little bit about where the sources of sample inefficiency come from if I have time to go over the proof sketch. But that's the important thing is that it's still providing you provably good global exploration for the linear MDP case. When you have finite dimensions, when you have infinite dimensions, the dimension gets replaced with an intrinsic dimension type quantity based on information gain of the RKHS, going back to this intrinsic dimension measure that was introduced in the GPUCB paper that won the Test of Time award this year.
Quick clarification question just for these slides. What's W, capital W here?
It's a norm parameter. So while I showed norm less or equal to 1 in the NPG W fitting procedure, more generally we allow a hyperparameter capital W there, and that's so it's just a norm parameter. Anything else?
I guess, how does it translate to the tabular setting, this bond?
So D will be SA.
Right. And how about the norm parameter? You want to compete with
that is probably that is
maybe that's not.
Yeah, I mean it's going to be either root SA or root SA times the horizon. I think probably root SA.
Yeah.
It's not bad.
Okay.
It's not bad.
Yeah. Somehow the norm needs to grow, but it's not that bad.
Yeah.
Okay.
I have a question actually regarding this.
Right.
So if I think of a pure exploration problem where reward is 0.
Yeah.
And so I'm wondering if I can use this algorithm to
have
pure exploration. So how long does it take to find the mixture of policies that would give me a distribution with minimum eigenvalue that is bigger than some constant?
Yeah, so basically the nice thing is because we are doing when we run the actual optimization, it's the bonus augmented reward. Even if you plug in reward equals 0 and drive the algorithm purely with bonuses, it will keep basically finding new directions till it can, and when it cannot, it will stop. And we had a reward-free exploration corollary at some point, and we do plan to bring it back again. We kind of we wanted to get the paper up on archive, and the corollary needed cleanup, so we just don't have it in the archive version, I think, at the moment. But we know how to prove it. And we actually have, if we get to the experiments, we have experiments as well in the reward-free setting, and the algorithm does do quite well.
So do you remember the rate?
Oh, the rates are terrible here for everything. So the rates are like, I don't know, I have epsilon to the 11 or something, 1 over epsilon to the 11, I think. Right. So the precise rates are terrible. Again, there is a separate work in progress on improving the rates, and those improvements will certainly probably bring it down to something like 1 over epsilon to the cube, 1 over epsilon cubed or something. But we are still checking the details of that.
Okay, thanks.
Yeah, but at least the algorithm continues to make sense in the reward-free setting, and we can verify that. Okay, so then now I want to talk about really, I think, if in some sense, if this is where we stopped, you should ask me, so what? Right? Because, okay, fine, you did something with policy optimization, but look, Chijin gives much better rates for linear MDPs and, has a simple algorithm, and everything's fine, right? Like, why do we need an algorithm which has a atrocious dependence on epsilon? Okay, it goes to infinite dimensional RKHS, but is it kind of really worth it? And, do I really need to add exploration to every model-free method? And, those would all be valid valid concerns. One of the reasons we were particularly interested is because we knew that NPG itself had this epsilon bias type term, which happens when we are running it in the non-exploratory setting. We wanted to understand what kind of robustness to misspecification will we inherit from these exploratory policy in these exploratory policy optimization approaches, and that's really the place where I think it provides some interesting extensions to what we knew before. So as before, we're going to make this expressivity assumption about how well we can fit the Q functions of the policies we find using linear functions in our features. And now I'm describing the assumption a bit more concretely. So the main twist in this is, so if I think about, what is the problem I solve in order to obtain WT, I do this linear fit for QT, but under the state action distribution that pi t induces, starting from my policy cover. So that's my fitting distribution. And if I put that fitting distribution here, then this would be the usual, statistical approximation error notion that we are used to seeing, right? And that would be a dependence on that would just simply ask, okay, you're solving a least squares problem, you have some approximation error in that least squares problem, how much does that hurt you? Because this is reinforcement learning, and we are not just worrying about a fixed distribution of our data, things end up being a bit more interesting. Rather than paying for the approximation error in the fitting distribution, you end up paying for the approximation in the state action distribution induced by pi star, which is the policy you're trying to compete with. It's the comparison policy. And it's a state action distribution you don't have access to, you don't have any control over. So this is a bit of a leap of faith, right? This is saying that maybe I have a small approximation error under my fitting distribution, and I hope it continues to translate to a small fitting error, small approximation error also under the state action distribution of pi star. And the reason this happens, the reason you care about this quantity under pi star is because if somehow you had the property that the direction WT you identify produces really good estimates of QT on the state action distribution of pi t, but it's completely out of whack on pi star. What can happen is you think you're improving the policy globally, but you're actually completely messing it up in places where you actually should have improved if you wanted to find descent directions that will take you closer to pi star. And the way this error manifests is is pretty simple. The same theorem as the well-specified case, but now we add this bias term with a horizon scaling to the policy suboptimality. So as long as this error is small, I know this algorithm can do something interesting. And now the main exercise we have to indulge in is, well, when is this condition satisfied, right? When is this thing going to be small? Is it going to be, first of all, small? Somehow, I've already maybe suggested that for linear MDPs, this thing should be small because I gave you a result without epsilon bias in the linear MDP case. So let's first talk about that, right? One property we know is that if I can point-wise express my Q functions as linear, then it really doesn't matter what is the distribution I measure the error under. I can just find the parameter WT, which has a uniformly good fitting error everywhere under in a pointwise sense, and it's going to have a small fitting error under all possible distributions, both under pi t and pi star. And just that simple fact tells you that epsilon bias is 0 for tabular and linear MDPs.
So just to clarify, this WT is not the W that is used by the algorithm, but this is like an ideal object.
Yes, I should have probably put a star there. Yes, right. It's an ideal object. So what WT star, the ideal object I'm looking at here is, so instead of solving the problem approximately with sample-based expectations and numerical optimization, if you minimize that expectation exactly and took some argument in that least squares problem that we wanted to solve, and you plugged in particular the best possible argument for pi star, okay, then what happens? And because I know that there is one argument which is going to have just a pointwise good approximation to the Q functions of pi t for linear MDPs, I know that this error is going to be 0. Yeah, so thanks for that clarification, Gurgo.
Perfect, thank you.
Okay, but if again, like, so far I've not told you anything we could not solve before. Sorry, was there any question? Any other question?
Just small questions, but I think it's clear from what you said. So
okay, so let's go to more interesting things where which is not where epsilon bias is not going to be exactly 0 in an obvious manner. First example I want to talk about is state aggregation. I borrowed this figure from Mengdi's paper on doing state aggregation for I think taxi drop off and pickups in Manhattan. So in state aggregation, the problem is that we have some large state action space. We want to map the state action space into some small discrete aggregated state action space Z, where Z is finite and has a small cardinality, and phi is going to be that feature map. It takes a state action pair and maps it into a discrete space now. And usually what we care about is an aggregation error. Okay, so when can we aggregate two states without any loss? Well, clearly, if I'm omitting rewards here for conciseness from the slide. So let's just think about the dynamics for now. If I take two states, two state action pairs, sorry, that induce the same forward dynamics, then aggregating them is sort of lossless. In general, I can measure my aggregation error as, let me look at all the states which are being mapped to the same discrete value of Z. And let me ask, what is the largest total variation in their one-step dynamics in the forward distributions? Okay, and similarly, you can include a term about the error, the difference in the absolute difference between reward functions. Right, so we have this aggregation error for that we incur potentially in any aggregate state Z. And what you can show, the bias, the epsilon bias quantity PCPG incurs is bounded in terms of this epsilon Z in the following manner. So draw a state from the distribution again of the comparison policy pi star. There's a max over actions of this epsilon of the features. So features of state action pair is going to be a discrete state now. So you look at basically if you forget the actions for a moment, you're looking at the expected aggregation error for the states that pi star visits, scaled with a horizon squared term. And the reason this is interesting is if we look at a lot of typical works around state aggregation, you often pay the L infinity of this state aggregation error. You look at the maximum error across all Z that you pay. And here we are able to replace the max over states with an expectation over states, which can be quite a bit more favorable in some problems. Of course, in the worst case, it's not going to be any better necessarily. And that's sort of one, in general, useful thing this epsilon bias sometimes will do oftentimes, because there is an expectation under the state action distribution of pi star. It will often let us take something which we might have paid in infinity norm before and let us get an average case version of it, although the average is under a distribution that we don't have a priori control over. One remark I want to make is that, okay, really what the ideal dependence here should be 1 over minus gamma, not 1 over minus gamma squared. And this is happening in our particular thing because we are doing everything with bonus augmented rewards. If we didn't have to worry about this, the bonuses, we would truly only pay 1 over minus gamma. And then Russo has some nice recent work on this as well, specifically for state aggregation. Questions about state aggregation? Okay, so the final example I'm going to talk about, just maybe in the interest of time. Oh, shoot, we're actually on time. Okay, so the final example I'll very quickly mention is you can have situations where a subpart of your MDP satisfies the linear MDP assumption. There is another subpart of your MDP which is kind of completely unstructured. It might even be an exponentially large search tree. It turns out, if, so this is kind of a strong condition, if the features of anything in the linear part are orthogonal to features of anything in the nonlinear part, then for any policy pi that stays purely within the linear part, if you try to look at the approximation error under its state action distribution, the epsilon bias is 0. Why? Because you stay here and you measure the linear fitting error here, and that's going to be 0 because there's linear MDP. Which is, it seems kind of trivial at first, but if you step back and ask it ask what it implies that PCPG can basically take your MDP, and if there is a nice sort of linear subpart of it, it can compete with any policy that never leaves that linear subpart. Right, so that's kind of a nice, maybe baseline guarantee you can have in many cases. And in this type of situation, you can actually also show that if you directly do optimistic Q-learning type approaches, because they will do Bellman backups from both the structured and the unstructured part of the MDP, they'll actually provably fail. So that's kind of an interesting point of contrast. I want to take 1 final minute to just give a very high-level proof sketch because I think people will appreciate it here. So the main thing we have to ensure is, we make progress. So we know that whatever current policy cover we have, NPFG will optimize well within the support of that current cover by previous theory. What we do is we basically, just for the proof, we build this usual kind of augmented MDP with an absorbing state, or in this case, we actually give ourselves absorbing actions in every state, and we say that, okay, so you have the policy pi star you're trying to compare to. Now in the modified MDP, you run pi star by taking if pi star ever wants to take an action such that the state action pair is unknown, force pi star to take this absorbing action a dagger instead, and a dagger takes you to a rewarding state. And this pi star is always operating within the support of our cover. So we can always compete with it. We also remember that we have bonus on unseen states. And now we can do the usual combination of optimism and explorer exploit results. So what we know is that at each iteration, NPG will either find a new direction by visiting something unknown, in which case we make progress, we are happy, or it will find a policy which competes with the modified pi star. And the modified pi star is always optimistic. So if you can compete with modified pi star, you also compete with pi star. And then, you just have to do some careful bookkeeping of your errors, as well as you have to make sure that you cannot keep finding new directions all the time, which is the usual control of these quadratic, inverse potentials we've seen many times before, so that you can just invoke to bound the total number of iterations the algorithm makes. And that's that. Final word about sample complexity. like I said, we have covariance estimation for designing the bonus. We have critic estimation in the NPG update. Both require samples. And there is really room for improvement in both in terms of better design of how and where we collect the samples for doing covariance estimation, how we handle the concentration, as well as currently the critic fitting does not do any data reuse at all. It kind of, it's completely on policy. So every time, for every NPG update, it will collect completely fresh samples, and that's pretty inefficient. The reason we are not doing a TD style fitting, which will obviously do data reuse easily, is because I don't know how to give the same kind of epsilon bias dependent approximation errors for misspecified cases there. Why? Although everything would be fine in the linear MDP case. But we do have better ideas now about data reuse. And in the interest of time, I'm going to stop there. Sorry for going a few minutes over. And I can take maybe one quick question before I have to really go. Thanks. And that's a link to the paper.
Thanks very much. This is very nice. Well, I guess the most obvious question is, like, do you think that this idea of this policy cover is here to stay? I mean, is it like absolutely necessary for algorithms to work in this setting, or this is really just the foundation that you used for constructing this algorithm, but maybe it's possible to get rid of it eventually?
Look, I mean, I'm a strong believer in the idea. I've used it for designing, agnostic contextual boundary algorithms. I've used it in other settings as well, beyond just, policy optimization for exploration in RL. I think it's the way I think about it is you can almost think of it as a dynamics model for the MDP constructed through the lens of a policy class. I think when we are talking about working with parametric policies, it's a very natural idea to think about. And it's an idea that really, even though I didn't have a chance to go over the experiments, one thing I will point out is that even if you take something like, let's say random network distillation, which does do reasonably well empirically, then what we find is, yes, we can replace the bonus in random network distillation with our bonus, and that will do something. But adding policy cover or not is a much bigger difference in whether your algorithm basically exhibits these catastrophic forgetting problems or not. And so I think it's actually a pretty important idea. I think it's here to stay. I think we'll actually see it more and more.
Yeah, I just wonder, like, how different it is from just, say, reusing all the past data that you've seen in all the past policies, right? I guess it's definitely related. It's maybe, I mean, I guess I like it algorithmically because it's maybe giving us a more concise description of that data if we can, distill that data into a small number of policies somehow, right? So if we can, in particular, keep the policy cover to be of a tractable size always, which is not necessarily, something we are focusing on in this particular paper, but we have looked at in other cases. Yeah, I'm just saying that, like, intuitively, the distribution of the data that you're getting from this policy cover is the same as if you just kept all the data and did just all your regression on all the past data, which is like, something that is like...
No. This is... Yeah, I guess it's related. It's certainly, okay, it's related. I guess you could sample states and actions from the replay buffer and do rollouts from there or something. It's, again, like if you just think about, think about practice and forget kind of theory land for a moment, then one of the things is, okay, you want to reset to a particular state action pair and observe a rollout from there. Well, how are you going to reset your agent into a particular state action pair? That's not always obvious. How you sample a policy from the cover and execute it is always obvious, right? So in that sense, it's more algorithmic, I would say.
Right. I understand.
Okay, sorry, I really do have to run now.
All right, so I guess we're gonna get into like all the delicate questions.
When's gonna handle the hard ones now? I guess.
He's gonna stay for the crucifixion. But thanks very much.
And thanks for the discussion. Yeah. Bye.
All right, I'll let you know if there are some outstanding questions.
Perfect. Thanks.
Thank you, Alekh.
Yeah.
Yeah, so I guess there's a bunch of obvious questions regarding the relations with Polytext. I don't know if I should ask those or pass it over to the actual Polytext people that can probably like draw the comparisons better. Because eventually, like both algorithms do like very similar things, like do like exponential updates to the policy with Q functions that are trying to estimate like the actual Q functions of the policies that you're running, right? And the difference is that in your guarantees you get this epsilon bias term, but as Alekh was saying, this is a bit of a leap of faith, right? To hope that this is actually going to be small. So I'm just wondering if, is this just a superficial connection between these algorithms, or there's something fundamental that I'm missing? I don't know, Csaba, you look like you want to say something.
Well, I don't know. Maybe I let Ben say something first, and then I can also say something. But clearly the updates are kind of the same, and then the analysis are going to be similar up to one point, and then they're going to diverge. Well, I can say that in Polytech, sadly, the exploration component is missing. It's not doing any clever exploration. We had some hacks that we added on the top of it. And because we wanted to have an elegant solution, but we didn't figure out any elegant solution. We didn't move forward with that. And so in this regard, if you look at what's the increment compared to Polytech, to me, the biggest thing is this, the use of the exploration bonuses, the use of the past data. I mean, I need to understand the details of the paper. And of course, when we are working in Polytech, we usually try to push the continuous setting, which is a nightmare. So maybe just giving up on that and then having resets also helps. But I think that the biggest thing is that the exploration bonuses are made to work here in some way. But and also, I don't know how much data reuse you do at the end, man. Maybe you can comment on that.
Right. Yeah. Yeah, so I guess it's definitely very similar if you just look at, in the terms of the policy update procedure, right? So both approaches are sort of doing this incremental policy update. Polytext is sort of doing, follow the regularized leader type of update, or you just could do exponential update as well, like a mirror descent as well, right? But I guess the main difference, as Csaba said, we starting from a fixed initial state, right? So which forces you to do exploration, and then we use this policy cover to sort of represent the region that are currently being covered. Okay, but we need to do exploration so that you can discover new state, right? You can discover new distribution. So we do that by adding reward bonus, and now you can do MPG using the cover as the the reset distribution, right? So the reset distribution is nice because now somehow with probability 1 over h, your agent will be on the frontier of the cover. Right from there, you just roll out and policy gradient just going to succeed, right? Because you have large bonus outside of the cover. So that's how we do exploration. And if you do exploration successfully, right, you basically guarantee to find a new policy whose state action distribution looks a little bit different from all the previous ones in the policy cover. So then you guarantee explore, right? Like in linear MDP, how many significantly different distributions you can get? There are at most d many times, d many such kind of distribution, right? Because if you look at the linear MDP structure, you can show that the state distribution actually lives in a d-dimension subspace, right? Any policy's state distribution can be represented by a linear combination of d vectors, right? So if you start doing those, if every round, I guarantee you find a new distribution that is different from all the previous distribution in the policy cover, right? How many times you can do it? At most d times, roughly, right? So that's roughly the idea about this exploration and why we want to keep the cover, right? Because we really want to find something that is new compared to all the previous policies distribution in the policy cover.
Right. Yeah. So there's one argument that maybe I'm not fully getting in here in Alekh's slide, which is that well, you're either beating pi star, or like, well, you're either beating like this policy that is allowed to go to heaven, right?
Right. Yeah.
Or you're discovering a new direction. But I guess this also, like, you know, beating pi star, it also like factors in this initial state distribution that is changing over time, right? So maybe just because you're beating pi star on this particular initial state distribution, does that mean that you're really beating the optimal policy from the true initial state distribution? Like when you have some very weird function approximation, maybe this can cause some problems.
Right. So I think the initial distribution, when you look at the objective function, the initial distribution is always the fixed state S0. Like if we only consider, you know, optimism under that initial state, it's just when you do policy optimization, you roll out from the distribution from the mixture of the policies and the policy cover. So the optimism, whenever we talk about optimism from this absorbing MDP construction, it's always under like VS0.
Oh, I see. Right. Okay, gotcha. Because for a second I thought that it's from this like policy cover. But
right. I mean, the policy cover is really sort of trying to make sure that you can fit the critic, you can fit the Q function accurately, at least inside the known set, right? So outside of the known set, if you just think about absorbing construction, outside of the known set, I know 100% what the Q function is, right? Because it's just 1 over 1 minus gamma. Right. And inside the known set, I can fit it because, you know, it's a cover. So that basically says that I can understand all the Q values for every state action pair, so even outside of the known set because of the absorbing construction, right? So I can just run, you know, policy iteration, approximate policy iteration, not approximate, soft policy iteration, right? So that's basically the intuition. But, you know, in the algorithm, we don't want to build absorbing MDP. So that's why we add, you know, this big reward bonus, which is like 1 over 1 minus gamma, that simulates, that is sort of simulating an absorbing effect. But in the analysis, we go back to the absorbing and we do the analysis in the absorbing. But you can, of course, do the absorbing in the algorithm as well, but not sure, you know, how practical that would be.
Right. Thank you.
Do you have some other question about the spatial linear models? Because I guess like you want to use that to highlight how this is different from the standard bonus-based approach or whatever, right? But I'm not sure I understand in what way this algorithm like is going to avoid exploring this big bad part where only some tabular representation is available, and like why it has a bias towards the linear part. Is it because the cover argument that you're using, that you basically keep a mixture of the previous policies, and so somehow that acts as a bias for the algorithm, and so if the algorithm ever gets to the linear part, then it likes to stay there because it kind of discovered that there is reward there. Is that how it works? Do you have some theory results that show that, like, you know, partial linear models, like I don't know, like the sample complexity in such and such? Was this on the slide? I guess it was not.
Yeah. So I think. So I think the key assumption there is that for the linear and the bad, these two components, their feature needs to be independent. Okay, so that because you know, you update it in the bad model, you want to affect, you know, their predictor in the linear model, right? And if that is the case, you can definitely get a sample complexity bound, right? So you can say that you can compare against the best one that stays inside that linear component. Right, because we, like, when we estimate the critic, right, we always just do roll out. We never do this Bellman backup, right?
Yeah.
So even if you're in the bad component, you just do roll out. You get an unbiased estimate of the value.
So I guess that's the big difference to all the bonus-based approaches, which somehow cook up the bonuses that make you go two places that you haven't visited, but here you're doing the rollouts, except that there was this little thing that like if they're untried action, then you always prefer to use those. So I was wondering how, despite that part, you're still avoiding going too often to the bad part. Because like, like the fringe evolves both in the bad part and in the linear part.
Right.
But they're competing with each other. But I guess maybe the algorithm is spending a little bit more time on the linear part, if it's initially had a positive probability of entering that part or whatnot.
Right.
But I still don't get like how the time is split between the two parts. Because in theory, I'm like, yeah, the algorithm doesn't have any built-in biases. It doesn't really know about any of this. So like, how would it be able to tell? And it could be that in the linear part, there are actually no rewards. And in the bad part, there are some rewards that look promising. And then you're attracted there, and then you don't even
Yeah. So note that we're not saying that we compare against the best policy. So your best policy
sure.
in the bad part, right?
No, but I meant that the algorithm is not seeing the rewards for a long time in the linear part. And eventually there are some rewards to be discovered, but like it takes hard work. I guess you should be thinking about, are we thinking about the asymptotic terms here, or are we thinking about like what happens in the limit? I guess in the limit, the algorithm goes everywhere.
Right. Yeah.
But maybe the bad part is infinitely large, and if the bad part is infinitely large, tabular MDP, then that's kind of like a hopeless thing. And if the algorithm spends too much time there, then it will be slowed down too much, even to compete with the best linear policy. So there's too much distraction happening. Could that happen? Or that's exactly what you're saying, that's not going to happen.
I don't think that's not going to happen. Okay. Yeah. I think the issue is that I think the key thing is this like for this policy cover, right? So you have a policy that with probability half it's gonna go to the linear part, with probability half it's gonna go to the right part, right? So whenever you're picking that policy, so you have like whenever you sample a policy in the policy cover, you always have non-trivial probability of sampling that policy, and you will have probability of going to the linear component. Like your probability of rolling inside, like rolling out when you roll out, rolling inside the linear part is always reasonably big.
Yeah, I guess the question is like, what is really the final output of this algorithm? Because you like go through like a bunch of policies, but like, do you just output the final one, or like just a mixture policy, like all of the past policies?
So after you do like n iterations, you find n policies and you pick the best one among them. So
right.
I mean, because we cannot really guarantee the last iter converged, right? So like you either do mixture policy or you find the best one.
Right.
So basically for this partially linear model case, you can see that we find at least a policy among all these n policies that competes against any comparator subject to the epsilon bias under that comparator's distribution. Okay, so it's really any comparator, right?
Mm-hmm. Mm-hmm.
Yeah, I mean, we definitely can't compare against the best policy, which could potentially deep inside the bad part, right? And there's no way we can do that.
Right, and there was some discussion, I guess, in the chat regarding how these bonuses look like, and do you really believe that it's the right approach to use this kind of 0 or max kind of bonus, or maybe there's ways to improve that? Like, can you update us on like what is the final conclusion of this discussion?
Yeah, so I think the short answer is that we don't know how to do this the usual linear band-aid bonus here. And what we're really doing is this absorbing MDP, right? In the analysis, like we completely just construct absorbing MDP and do the analysis there.
Yeah, but
And
like once you add these absorbing states, then you're no longer in a linear MDP anyway, even if your true MDP is linear. Right?
So there's a trick that Alekh did not really mention, and that was actually a bug that we had in the very original version, but we fixed it very quickly. So with this reward bonus, even with this indicator reward bonus, right? So your Q function is definitely not going to be quadratic, but sorry, your Q function is definitely not going to be linear, right? Because you have quadratic type of bonus there. But the nice thing of linear MDP is that regardless of what value function you have in the next time step, right? If I just apply this transition function, I get a linear thing. And now what I can do is instead of fitting the Q, which is definitely not linear anymore, I can fit the Q minus bonus, which again is the linear, right? So then I get a perfect generalization arrow, and then I get I add the bonus back. So that is my critic. A linear function plus the bonus is my critic. So that's what we did eventually. Yeah, and
so you do linear MDP case, but you also like do some version of it for general MDPs.
Right. So for general MDP, we basically do this epsilon bias under this regression target, which is Q minus bonus. Right. Which, I mean, in some sense it's reasonable because we know that the bonus is definitely not going to be linear. So maybe we should just, but it's a bonus that we constructed. So we know the bonus everywhere. So why don't we just, fit a Q minus bonus and then plus bonus back? Yeah. And then the epsilon bias is measured under D star with respect to this new regression target. Right. Yeah. And in the experiment, we did this like the usual linear band-aid bonus, and it works pretty well. But we don't know how to prove that. And I think this bonus thing is a bit weird because like so one reason that we're doing we're not using it is that we're doing this infinite dimension RKHS setting, right? So even if you stick to model-based version, this UCBVI version, if you're trying to do this infinite dimension, it's really hard to do that because of the covering argument, right? I think if you're familiar with this linear MDP analysis, then you will see like we have to do cover on all the possible value functions that will that can be encountered during the algorithm, and you have to do covering on this quadratic bonus.
Yeah, which is insane. And now you have to, but I guess like one limitation is that you still can only handle finite actions, right? If you would have infinite actions, then this would also
so this is related to the mirror descent analysis, right? So the reason that we do finite and pay log A is because this is the range term in the mirror descent, right? There's a KO divergence between the uniform distribution and the comparator's distribution.
Right. Yeah.
I mean, if you give me a continuous action space and you give me some initialization that has bounded KO, then we're fine. You're just going to pay that range term.
Okay. Yeah. Sorry, I thought I also remembered some polynomial terms in A.
That's in Alekh's first component, first part. I think there what they're trying to do is so that's in his first integer part result, right? I think they're paying some poly A there because they are fitting Q functions, but all you really need is the advantage function. But fitting Q functions, in order to get good estimation of A advantage, by only fitting Q, you need to act randomly. Like you're loading in with our policy and then uniformly picking an action, right? Because Q only corresponds to one action, and you wanted the advantage to be accurate, so you have to pay this poly A.
Right. Yeah. And your bonuses, like this kind of discrete bonuses, so these are state-wise and not state action-wise.
No, this is state action-wise.
Right. Okay. So then it's not really tractable for infinite actions, no?
It is really tractable, yes.
Is it or is it not? Because I can see like evaluating a linear function if you have like or a quadratic function even.
I mean, okay, so the part of the algorithm that is most suspect for the infinite action case is when you're forcing exploration when you have unseen state action pairs. You can probably do something about that, but it's not trivial probably to to the extension there. Right. I mean, it's not the tractability, but it's like the analytics. Like, how do you deal with that?
Yeah, right. I mean, not that I care that much about this infinite action case, because otherwise you would have to like optimize this linear function, or like, you know, this inner product between like the feature vector and your parameter vector, and even that can be hard, right? Especially if you have this kind of quadratic function, that also can be hard.
So regarding this RKG system, like infinite dimensional stuff and bonuses and UCB VI, RSVI, can't we just give up on data reuse, get crappy error bounds, and then get home with like just be done with it? Like, we could do it, right? Just get crappier bonds without reusing data.
Right.
I think that the reason you're running into this trouble of with the covering arguments is that because we are trying to get optimal dependencies on everything.
Right. Yeah. So I mean, we get rid of this this covering argument, but at the cost of, you know, pretty bad polynomial dependency, right?
Yes.
Because we're really doing on policy, and we are not doing like any Bellman backup using the previous collected data.
Yeah. So I was just wondering that, okay, then the bonus approaches could also do that. It's elegant, no? Would it work? Well, to some degree. Yeah.
Right. I mean, we did try it. I don't remember what exactly happened, but we were stuck at somewhere. But then we switched to absorbing MDP.
Maybe
so we first did absorbing MDP, then we realized, you know, oh, we don't really need to do absorbing in the algorithm, right? It's just an analysis, you know, trick. So we can just enlarge our bonus to be like, you know, 1/1 minus gamma, and then only do absorbing in the analysis to make the algorithm a little bit more practical. So that was the story.
Anyways, I think it's pretty cool.
Yeah, I mean, Alekh, they also are working on some follow-up where they're using importance weighting trick to do data reuse. And I think they were doing some trajectory-wise importance weighting, because you still want to get sort of maintain this on-policy nature, because you still want to be robust to model specification. So you can't just run like least square value iteration, and because if you do that, then you're immediately going to pay something like L infinity approximation error in a state abstraction, for instance, right? Yeah. So they still want to maintain on-policy nature, but you know they do some other trick. I don't really know. Yeah, I'm not involved in that one.
Okay. All right.
Yeah. I mean, our polynomial bounds are terrible, but I personally feel like this this average model misspecification thing under this state abstraction example is pretty interesting. Compared to, you know, the previous work that use model-based or like, you know, Bellman backup-based approach. Like, we don't have a lower bound to show that you definitely have to pay L infinity error. It's just, you know, the existing results always have. I mean, my personal feeling is that, like, Sham and I tried, we can act like, if you just want to derive a lower bound for a specific algorithm, right? So if you want to derive L infinity lower bound for a specific algorithm, that is doable. But like in general, what we can see for like, you know, model-based or Bellman backup-based data reuse algorithm, that we don't know how to do it.
What do you exactly mean by this? How would an L infinity lower bound look like? Can't we do it in brackets, by the way?
If you just stick to like a specific algorithm, I mean, we don't have anything right down here. But if you just look at one particular algorithm, for instance, like UCBVI maybe, right? And you have model misspecification, you have this data abstraction. So I think you can construct an example show that you have to pay L infinity. Like your approximation error at the end is L infinity error.
I mean, we do have a lower bound in our paper that is at ICML, this good feature something reinforcement learning for the unrealizable case that has the approximation, infinity approximation error in it. Yeah. That should, every algorithm has to pay it. For bandits, it's easy to do. I mean, like, it should generalize to MVPs. Yeah.
So do you think that there's eventually like any hope in replacing that pi star in the definition of the bias with something else? I don't know, like pi t or some mixture of pi t and pi star?
Oh, you mean like a transfer error? Not, like instead of talking about distribution shift, you just do like, just pay a generalization error under a training distribution?
Yeah, right. So how well can I approximate the Q functions that I'm seeing during training?
That I have no idea. I mean, that seems pretty hard.
Yeah, right. I mean, like, is that enough to guarantee that I'm going to converge somewhere good? It's like, is it enough for me to make sure that I can approximate my own Q function as well on my own distribution? Or is there some other condition that I need to make?
Intuitively, that's not going to be
possible to converge towards the optimal policy.
I mean, intuitively, that seems not enough, right? Like we know from approximate policy iteration, like you're just gonna oscillate between like two policies if you just do that. I mean, like every iteration, I can guarantee you get a good Q estimate under your current distribution, right? So you just act greedily, like a approximate policy iteration. You're never gonna converge.
Yeah, sure. Well, I guess like the biggest problem that I see here is that, you know, if Q star is not within your class, right? And maybe you're like happily evaluating your policies and, you know, you're seeing that all the errors are small and then you're like, oh, I'm doing well. And then you make like small improvements, but you're getting nowhere near the optimal policy. You're stuck somewhere. Like what is, I don't know, like how can you quantify this effect in your analysis? Because I guess like here you can just replace this pi star with pi t, and then just assume that this likelihood ratio is bounded between the state distribution of pi t and pi star.
Right.
And then like you can make those errors as small as
right.
one.
I guess if you assuming the concentrability coefficient is bounded, then you can get something like, you know, this coefficient times your generalization error, right? So you can quantify that maybe in that way, but it's unclear. Like, you know, like how can I know the upper bound of my, you know, concentrability coefficient?
Right. Yeah.
That's actually a L infinity type of thing, right? It's a superior over OS.
Yeah.
But yeah, I'm also curious, like what type of agnostic result eventually we could get.
Yeah.
I mean, it seems that this CPI type of style result so far is kind of strongest.
Yeah.
And at least when I'm teaching this RL course this semester, like, you know, CPI, we went through all this like approximate policy iteration approach. CPI, I don't know if there's other new approaches nowadays, but CPI seems, the guarantee seems still kind of the strongest agnostic type of result we have. Right? So you only pay the concentrability coefficient, which is like, you know, your comparator's distribution over your initial state distribution. But API or something, you have to cover all policies state distribution, right? Yeah.